Hello, and here we are again, talking about AP Chemistry. This time, topic 7.9, Introduction to Le Chatelier's Principle. So, Le Chatelier's Principle is all about applying stresses to systems that are at equilibrium. So, I am going to kind of give you an example of equilibrium that has a little bit of everything. So, let's say that you have substance A, and I'm using the sparkly pen again, even though my wife hates it, because I like it. So, anyway, substance A reacts with substance B, and A is a solid, B is aqueous. Once these react, they set up an equilibrium that produces substance C that's aqueous also, but a gas comes off of this reaction in substance D. Also, this is an exothermic reaction, so energy is also released in this process. So we've got substance A and B reacting, forming substance C and D, and some energy. What we want to talk about is once this equilibrium is set, in other words, once this reaction it has the same rate going forward as the rate going backwards, what happens if we apply a stress to it? And when we talk about stresses, we're talking about adding or taking away a reactant or product, so changing the species. And by species, I just mean one of the substances, a reactant or a product. So a change in the species. Or maybe a change in the temperature. We heat it up or cool it down. Or we change the volume of the system. Or we change the dilution. So these are all things that could be stresses to this reaction. So we're going to talk about each one and just see how those stresses apply. So first, let's talk about changes in species. When we talk about change in species, that means either adding some more reactant or adding some more product. Because concentrations of solids and liquids don't change, changing solids and liquids does not affect equilibrium. So if you change a solid or a liquid in a particular reaction, that is not going to change the equilibrium of the reaction at all. And when I say change the equilibrium, I mean make more reactant become product or make more product become reactant. So that's what I mean by a change in equilibrium. However, if we do change aqueous solutions like B and C, or we add or take away some gas, that is going to affect equilibrium. So if we add a species, that will shift equilibrium in the opposite direction. So for instance, let's say I add some B to this reaction. That means that we have more B that can react. It's going to react with some of the A that is still present, and it's going to shift the equilibrium to the right. It's going to shift and make more products because we have reactants. It's going to try to get rid of it. Le Chatelier's principle says whatever you do to a reaction, it's going to try to get rid of what you just did. So if we add some B, Le Chatelier's principle says equilibrium will shift to get rid of that B. So what does that mean? The equilibrium is going to shift to the right. We're going to make more reactants react and produce more products. What if we take away a species? Before we get there, what if I added some more C to this reaction? In other words, I stuck some more of substance C into the solution. Well, now that I have more C, Le Chatelier's principle says it's going to react and shift equilibrium to the left. It's going to make more reactant in order to get rid of that C that you added. What if I take away a species? So I remove a species. Well, then that's going to shift in the same direction that you applied the stress. In other words, it's going to try to replace what you took away. So for instance, let's say that we had this reaction and it made this gas and you vented off some of this gas. You let some of the gas out of the chamber. You just removed subspecies D. So the reaction is going to react to try to replace the D that you just released. So it's going to shift towards the direction of what you just removed. So it's going to try to replace it. So adding a species, it shifts in the opposite direction to get rid of what you added. If you take away a species, it's going to shift in the direction that you removed the substance to try to replace it. So that's what I mean by delta species. Delta temperature. So if you'll notice in this reaction, we know that energy is a product. It's an exothermic reaction. So if we add heat to this reaction, we heat up the reaction and increase the temperature, it's going to try to shift in the cooler direction. So if you look at this reaction, this is the side that has all the energy. If we add energy, add some temperature, heat it up, you're adding energy. It's going to try to get rid of that energy that you just added. So it's going to shift reaction to the side that doesn't have the energy. It's going to try to get rid of the extra energy. So in this reaction, it would shift left. What if we took away energy? And that means we cooled it. Well, then it's going to try to shift towards the hotter direction, the more energetic direction. So if we took energy away, if we remove some of this energy, then the reaction is going to try to replace the energy you removed. So it's going to shift to the right in this particular reaction. So changing temperature simply tries to get rid of the energy that you added or replace the energy that you took away. Volume. So volume only applies to gases, and that is it. It does not apply to anything else. So if we increase the volume of this reaction, in other words, we made the reaction chamber bigger, that means there's more space for gas to occupy. So by increasing the volume, we're giving more space for gas to exist, and so the reaction is going to try to fill up that extra space with more gas. So the reaction would shift to the right in order to make more gas. So make more gas. Whichever side of the reaction has more gas on it, it's going to shift that direction. There's more gas on the right, so it would shift to the right to make more gas. What about if you decrease the volume? Again, this is only for gases. Then the reaction is going to make less gas. It's going to shift away from the gas. So if you compress the gas, there's not enough room for the gas to occupy anymore. It's going to be pushed into the solution, and it's going to shift away from the gas to the products reactants in this particular case. So with gases, you always, if you expand the volume, it's going to make more gas. If you decrease the volume, it's going to make less gas. And then last but not least, what if you dilute a solution? In this particular case, we have two aqueous solutions on either side. If I increase the concentration, and I should have said dilution or concentration. If I concentrated the B, I had more B, so increase the concentration, then it's going to shift to get rid of that reactant. So it's going to shift in the opposite direction. So if I increase the concentration of B, it's going to try to get rid of that B that you added. So it's going to shift to the right. If I increase the concentration of C, then it's going to try to get rid of that C that you added and shift to the left. If we dilute the solution, if there's less, then the reaction is going to try to replace what you diluted. So if we used a more dilute solution of B, it's going to try to replace the B by reacting C and D. Okay, so that is a quick introduction to Le Chatelier's principle. I do want to point out just how you could measure this. And so one way you can measure is if this is an acid-base reaction, that means you have changes in concentration of hydrogen ions, either on the left or the right, then you could measure the pH of the solution to measure how the reaction is shifting. So for instance, if you had H positive being produced on the reactant side, then a shift to the right would be a decrease in pH because more H positive means lower pH. If you had an increase in pH, that means that your reaction was shifting to the left. So measuring pH could be a way to measure this. Another way you could measure this is by temperature. If you changed one of your variables and the temperature changed of your reaction, a higher temperature would indicate that you were making more product. A lower temperature would indicate you were making more reactant because energy is on the product side. So if more energy is being produced, the temperature would go up. If less energy is being produced, the temperature would go down. So temperature is another way we can measure this. And then the last one that I wanted to talk about was color. If one of these reactants were colored and the other ones weren't, like let's say that this side was colorless and this side made a red product, then you could measure the intensity of the color. If you had more red being produced, that means more product. The equilibrium was shifting to the product side. If the color was decreasing in red intensity, then that means you're making more reactant. You've shifted the reaction to the reactant side. So color is another way that we can measure how equilibrium is shifting in a chemical reaction. pH you can measure with the pH probe. Temperature you can measure with a thermometer. Color you could measure using spectroscopy or a spectrometer in order to measure the color intensity. So that's an introduction to Le Chatelier's principle, just talking about qualitative ideas about how Le Chatelier's principle and changes in concentrations, temperature, volume, and the species can change equilibrium. If you have any questions about this, please let me know. Good luck.